So up until this lesson, we've looked at motion just horizontally or just vertically. When we're talking about projectile motion, what we're going to have to keep in mind is that we have both a y and an x component to the motion for a projectile. So if you throw a baseball, throw a football, doesn't matter what it is. Throw anything. It doesn't matter. Throw this. Don't throw this coffee cup. Who would throw that coffee cup? Whatever you throw something. You know that it sort of takes a trip through the air that kind of has this arcing motion. It doesn't just travel straight X or straight Y. It actually does a little bit of both. You see it kind of go up a little bit, and so it means that is an increase in Y. It's going forward, whatever we call forward, so there's a change in X. So technically there's a change in both Y and X when we're talking about projectile motion. Alright, so that means it has velocity and it has displacement along both as well. So that's something to keep in mind. If you need to, I'd pause this video, copy these notes down. But these are very simple things, but you're more than welcome to do that if you want to. But let's go ahead and slide forward, and let's take a look at an example on this. All right, just want a free body diagram. We just want the basic concept here of projectile motion. So let's get a free body diagram. We got two projectiles. So we're going to do this two different examples. One where it's launched horizontally from a ledge, and then we'll do the second one. It's at some angle, and we're going to call it angle theta. It won't matter what the angle is. This is good. These free body diagrams are going to hold true regardless. Okay. So we have a ledge. So let's get a ledge. All right. Got a ledge. All right. Now we're just going to need something that's going to be launched from that ledge. It's going to go with. Just going to go with something that's circular. All right. So as soon as something is launched horizontally, so we're doing this one first. So it's launched horizontally. All right. Launched horizontally. So if we think about this, as soon as it's launched horizontally, it has velocity on the x. Okay. It has a velocity on the x. It will have some. And we know that what's going to happen is it's going to take a path that's going to look, it's going to look something like this, right? And of course, down here at the bottom, we call this ground, so that equals 0.0 meters, all right? So ground zero, so to speak. Doesn't mean it's fallen 0 meters, just that we're at what we're defining as 0 meters up from the ground. Okay. So we see it takes that motion right there. So now if you think about this, let me get this out of the way just because I want more room. We have here a change in y. There is a change in y here, and we have an equation for that. We have vi delta t plus 1/2 a delta t squared. Now we know that this is falling downward, so its downward acceleration is due to gravity, which would be a negative 9.81 meters per second squared. When it's as soon as an object goes into free-falling objects, we know that the initial velocity on the y equals 0, right? So that holding true, then we know that this equals 0. And so what we have is delta y equals 1/2 a delta t squared. Okay. So this is the displacement and the motion along the y-axis. Its initial velocity on the y-axis is 0 because it's in free fall. All right. And its displacement on the y-axis, we're familiar with this, with no initial velocity. It's just change in displacement, 1/2 the acceleration due to gravity, times time squared. So now we've got velocity along the x. All right, so let's think about this. We know velocity. Let's just go off to the side. Velocity equals your displacement divided by time, right? Well, if we come here, we still got displacement divided by time. Let me rewrite that again. Divided by time, right? Put that over here. And so both of those things are happening simultaneously. They're both happening simultaneously. It's moving, all right, let me try to do this. So initially it's launched, and it goes, and it'll have that initial velocity, and that velocity will stay constant in that direction. Along the horizontal direction, that velocity will stay constant. And the initial velocity along x, it's going to have to be greater than 0 meters per second if it's launched horizontally. It's just that it has no initial velocity going straight down. So that's pretty easy. All right. So let's take a look at what would happen if it were at some angle theta. All right. So if it's at some angle theta, we have a very similar situation. First, let's get our ledge. We have the object. I always forget to turn that thing off. We have our object. This time our object is launched in that direction. Now let's think about this. If we draw our eye to right there, some imaginary line, we can see that we have an angle theta right here. So whatever, it's launched at some angle in relationship to the adjacent side, which in this case is the ledge itself. So it's at some angle theta. So it's launched in this direction. So it has some initial velocity, and that initial velocity, right, along the y, it has to be greater than 0, right? It has to be greater than 0. So the initial velocity along y has to be greater than 0 meters per second. That's what got it up in the air in the first place, right? You should be able to see here that we have a triangle, right? Now, once this is launched, this thing is going to take a path that's going to then do something like this, right? It's going to do, let me come up here and do this. It's going to do something like this, right? There's our ground. It's going to do something like this. Pretend that's a straight line. We don't have to pretend. I keep forgetting. I've got this. That's really nice. All right. So it's going to take that arcing motion, right? It's going to take that arcing motion. So we've got initial velocity in the y that is greater than 0, and going along. Well, let's stick with one thing at a time here. So you can see here that there's going to be a change in y. There is going to be a change in y. Now, we already knew that the initial velocity times delta t plus 1/2 a delta t squared. So this holds true already, but now we have to account for the angle. So if we come up here and we think about this, our velocity along the y, so we've got delta x over delta t, right? So the only thing that's really different now is we have to account for what is happening along the y-axis. And if you look at your triangle, oh, that's more than I wanted. Let's go with, let's do this. If you look at your triangle, this side that's opposite I'll just leave that. There we go. We can see the triangle. The side that is opposite of theta, the y, that's a sine function. That is a sine function. Since that's the sine function, what we do is we come over here and we basically take the sine of whatever the angle is, and that is what is having an effect on the y-axis. That's what's happening in effect, which is affecting that time, because instead of it coming out straight and just driving this height, now it's come up this way, so it is a little bit higher, so that's going to affect the amount of time it takes to actually hit the ground. So it's sort of a multiplicative effect. So what we have to do, if we think about that, is we have to squeeze that into this equation here. So we get delta y equals vi sine theta delta t plus 1/2 a delta t squared. All we have to do is we're just factoring in the value of the sine. So now if you've got it launched at some angle theta, this is the only thing, it's the same equation, but now we're factoring in whatever that angle is for the y-axis. The same is going to hold true on the x-axis. So if we come back up here to our problem, we saw, let me separate out these problems here. We saw that on the x-axis we have delta x over delta t, correct? So if we come over here, then velocity along the x, if we have delta x over delta t, then the same is going to hold true here. We need something that is going to factor into that. And the side right here, along that adjacent side, that is our cosine. That is the cosine of theta. And so we have to just simply factor this in right here. And so we get a new form of the equation. Velocity on the x equals the change in displacement divided by cosine theta times delta t. So now we get this. All right. So, I'm sorry. If you were to look for the displacements, if you want to know how far it went, my mind wandered for a second. I heard a noise out the door, and so I was looking at the time to see how much time I actually had. Sorry. So let me erase this, get this out of the way for you. So let's think about this. If we were to solve for just the displacement, how far would this thing off? So it launches at some angle theta? Question mark. How far would it go when it hit the ground? Well, if we rearrange this equation right here, then we get delta x equals the velocity horizontally times cosine theta times delta t. So it's the same equation, I just rearranged it in two different ways. All right? I hope that helped. Do some practice problems, come back, take a look at this. Once you essentially get it, you draw your free body diagram, it basically becomes plug and chug for the most part. You just have to define all of your initial variables correctly. All right. I will see you later. Stay curious. We'll talk soon. Bye.